Hello everybody, and welcome to our second part on the Intro to Series. So in Lecture 18, we're going to be wrapping up our Introduction to Series, and we're going to talk about the test for divergence, and also another special type of series called the telescoping series. Okay, but let's build our way up to there. So first I want to start with a theorem. So this theorem says, if some series, sigma n equals 1 to infinity of a sub n, if it's convergent, then the limit as n goes to infinity of a sub n must be 0. So this is a condition that must be satisfied for something to be convergent. It doesn't necessarily, it's not the only thing that makes a series convergent, but it's something that must be true if a series is convergent. You must have this as true. So because of this theorem, we get our first test for series, and it's called the test for divergence. So let me state what it says. So the test for divergence says, if the limit as n goes to infinity of a sub n does not exist, or the limit as n goes to infinity of a sub n is not equal to 0, then the series is divergent. So the warning I have to give you right here, and I'm going to be reminding you of this a lot this semester, is this is a test that lets you know whether a series diverges. But this test will never tell you whether a series converges. So let me write that right here. I'll just maybe put that just under it. This test only tests for divergence, not convergence of a series. So if you're using this test and then your answer to the final problem is convergent, you've done something wrong. You can only conclude something is divergent using this test. All right, let's practice using it with a couple of examples. So here I have the infinite series of this right here. So you can think of this as my a sub n. And to use the test, you want to take the limit of the a sub n. So we'll do the limit as n goes to infinity of n squared over 5n squared plus 4. Because the powers match, the degrees match, you take the ratio of the leading coefficients, and this is 1 over 5. So 1 over 5 is not equal to 0. So that tells you that the original series is divergent. So as soon as you get something that's not equal to 0 for the limit, you conclude that the series diverges. And that's it. It is as simple as that. Often, though, when you try this test out, usually you do get 0, and then you have to try a different test. So if you ever get 0, try something else. Let's try this next example. So here's the series. This is my a sub n this time. So the infinite sum of this, we'll try our test for divergence. So we'll do the limit as n goes to infinity of the a sub n. We can just focus on the inside. So the limit as n goes to infinity, we have the same kind of thing that happened before. The powers are the same, so I get 1 over 2. So this limit is ln of 1 over 2. The only thing I need to know is that that's not equal to 0. So because it's not equal to 0, you say, by the test for divergence, this series right here diverges. Remember, you're only going to conclude something diverges. You're never going to conclude something converges with this test. How about this one? So we have arctangent of n. So let's think about this. We have the limit as n goes to infinity of arctangent of n. What does the graph of arctangent? This is probably just an excuse for me to remind you what arctangent looks like, to be perfectly honest. Arctangent of x, function of a real variable, it has asymptotes, horizontal asymptotes at pi over 2 and negative pi over 2. And it looks like tangent turned on its side, so it looks something like that. And if you go to infinity, you go to the right forever, it approaches pi over 2. So this limit right here is pi over 2. And pi over 2 is not 0. So this series diverges by the test for divergence. So this diverges. And then let's take a look at this last example. So this is a special series called the Harmonic Series. It's the infinite sum of 1 over n, as n goes from 1 to infinity. I've even wrote it out here as well, because I'm going to talk about this in more depth. But if you plug in 1, you get 1. If you plug in 2, you get a half. And you're going to add up all of those forever. So we're going to use the test for divergence on this and see what happens. So here's my a sub n. I have the limit as n goes to infinity, 1 over n. This is equal to 0. So you would not make the mistake here and say that this converges. You can't do that with the test for divergence. So because it equals to 0, you say the test for divergence is inconclusive. Basically, when you get 0, it's like a I don't know, and then you try something else. What students get confused is this. Let's talk about a sequence now. That's an infinite sum. This right here is a sequence. So that's a list of numbers. So this is 1 over 1. If I plug in 1, 1 over 2, dot, dot, dot. Like, so there's just a list. You're not adding these together. What's the limit as n goes to infinity as I just go on my list? So this is 0. So the sequence converges to 0. The sequence does. The series, when you put that summation in front of it, we don't know whether that converges or not because this test was inconclusive. But the sequence converges to 0 because the actual list of the numbers are getting closer to 0. All right, let's talk more about the harmonic series. It's going to be very important when we use this for other tests. So I'm going to claim that this harmonic series, it actually diverges. So it diverges even though we didn't get 0 over here. So let me show you why. I'm going to try to convince you why. So remember, S of n, so let S of n be the partial sum of this series right here. So S of 1 would be equal to 1 if I plug in the first one. That's the first term. S of 2 is equal to 1 plus, and then my second term is going to be 1/2. So I'm doing the partial sum from the last video. S of 4, I'm going to jump down to the S of 4, is 1 plus 1/2 plus 1/3 plus 1/4. That's still a finite thing. And if you look at these two, that's greater than if I had 1 plus 1/2, so keep the same two first terms, but replace this with plus 1/4 plus 1/4. Because 1/4 is certainly less than 1/3, and that's the only thing I've changed here. So this is certainly true. And then the thing on the right here is equal to 1 plus, and then I have a half plus another half here gives me 2/2. OK, so what? So let me jump down to the next one here, and you're going to start to see a pattern. So bear with me. I'm going to write a bunch. I have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, a 6. I'm trying to get all the way to the 8th term, plus 1/7 plus 1/8. OK? So this whole quantity on the left side, if I group these together like this, it's going to be greater than 1 plus 1/2 plus, I'll make these two 1/4 again, just like I did in the previous step. And then for this one right here, the 1/5, 1/6, 1/7, 1/8, that's greater than 1/8 added 4 times. So replace all of these with an 1/8, and you've got something. So this right here is strictly less than the thing I've got on the left side. I'm going to draw a giant greater than sign. OK, but what is this equal to? Well, this is 1 plus a half, and then here's another half. I have 4/8. So this is 1 plus 3/2. So at each stage I'm doing this, I'm increasing the size of my right-hand side by 1/2. And the thing is, I can continue doing this forever. I could do it for s of 16, but you'd probably get mad if I kept going. So I'm not going to keep going. But I'm just going to write, this process continues forever. So s of 2 to the n, whatever stage I'm at. So here was 2 to the first power, 2 to the second power, 2 to the third power. This is going to be 1 plus a half plus, you go all the way to the very last term, so this is 1 over 2 to the n. It's always going to be bigger than 1 plus, and then here, this 2 is the 2 squared from the 4. And this 3 right here is the 8, which is 2 to the 3. So that's where the 3 is coming from. So no matter what that n is right there, the actual sum, partial sum, is going to be greater than 1 plus n over 2. However, the limit as n goes to infinity of this thing I have on the right, that goes to infinity. I have 1 plus, this will go to infinity. So my partial sum is larger than infinity. So in fact, this is going to go to infinity as well. So s of 2 to the n goes to infinity as well. So if the partial sums go to infinity, that means that the original series, that had to converge as well, because it doesn't go to a finite number. So that's one idea of showing that this harmonic series diverges. We're going to come up with some other ways to show that as well, but I just wanted to get that out of the way because this is very important. And like I said before, we use this for other tests in the future. It relies on knowing this fact. OK, in the next part of this video, we are going to talk about another type of series called telescoping. And then we're going to do some examples. So I'll see you soon. All right, so now I'm going to talk about a new type of series, and it is called a telescoping series. So let's talk about that and give you an example. So a telescoping series, it contains many terms which cancel, allowing us to calculate the sum. A typical thing that happens is you use partial fraction decomposition. Not a lot, not like all the time, but usually. So I'm just going to write usually, not always, but usually, we use partial fraction decomposition, which we learned in the exam 1 period. So we use partial fraction decomposition in the calculation. So you should be good with that method. If you're not, you can go review the videos on partial fraction decomposition. So let's take a look at this series. So I would like to sum this series. The way you know that it's telescoping is you might see that you have some kind of polynomial on the bottom, and you can use partial fraction decomposition. So let's go ahead and try to break that up. So this is equal to summation n equals 2 to infinity 2 over n minus 1, n plus 1. So that's just using factoring the difference of squares. So this right here, using the decomposition, I know I need to have some a over the linear factor n plus 1, and I need to have some b over the linear factor n minus 1. I don't actually like the order that I put those in. I'm going to put n minus 1, and I'll put n plus 1. I reassure you that there really is no difference in the final answer. I just want to write it like that. And now we need to figure out what a and b are. We have the cover-up method, which works for linear factors, and these are both the highest power of that linear factor. So if n equals 1, you cover up the factor that goes to 0, and you have 2 over 1 plus 1 is 2. So a is 2 over 2, which is 1. And then if n equals -1, which makes this fraction undefined, you're solving for b. So if you plug in -1, cover up this factor, and you have 2 over -1 minus 1 is -2, so b would be -1. And what that means for us is that this sum, n equals 2 to infinity, this splits up into a is 1, so 1 over n minus 1, and then b is -1, so minus 1 over n plus 1. So that's what this series breaks up into using partial fractions. Now at this stage, what you need to do is you need to come up with a formula for the partial sum, s of n. And what I like to do is I like to use a table. So let me show you what I do. So here I'm going to write n, and then here I'm going to write the terms I'm examining. So this is 1 over n minus 1 minus 1 over n plus 1. And you're going to list some of these, and you're going to try to look for a pattern. That's the goal. So you plug in the first n value you have, which is 2. By the way, why didn't this one start with 1 like all the other ones we've seen? It's because if you plug in 1, it goes undefined. So they have to start at 2 for this. OK, so if you plug in 2 into this decomposition, you get 1 over 1 minus, and then 1 over 3. OK, let's move on to the next one. So if you have n equals 3, then this is 1/2 minus 1 over 4. OK, and I'm going to go to 4. And then if I plug in 4, I get 1 over 3 minus 1 over 5. And I'm going to do one more just to show you, because remember, we're supposed to sum up all of these when you're done. So summation means you add up this plus this plus this. You'd add those all up forever and get an answer. Let's do the fifth one, which is 1/4 minus 1/6. And this continues forever. Now, you're looking for some kind of pattern. So what I notice is that the first cancellation I see is here and here. Those two cancel out. And that's kind of the pattern that we get the cancellations in. And then here you have this one and this one cancel out. So what you need to do is you need to ask yourself the question, how many terms did it take for you to see the very first cancellation? And we had to do 1, 2, 3 of them. So we had 3 terms, 2, 3, and 4, before we saw that first cancellation of the 1/3. So we did 3 terms before any cancellation. So once you have that, you now know how to get the partial sum. So what you're going to do is you're going to do another column. So you're going to start with n. And you're going to need to do 3 more because it took 3 cancellations. You start with n, and you work backwards. So it'd be capital N, n minus 1, and n minus 2. So you're plugging in new n values. If you plug in capital N, you just get the formula with capital N's replaced. If you go backwards 1, you get capital N minus 2 minus 1 over n. And if you go backwards 1 more, you get n minus 3 minus n minus 1. And then if you notice here, once I've done that one, you have this cancellation and this cancellation. So this is like the beginning, and we went all the way, and this is the second column, we went all the way, and this is the final one, the final term that we got to. So you imagine now thinking, what happens all the way up? Well, if you start with this term, for example, you go over 1 up 2, and it cancels with that pair. So this one, assuming we have all the ones higher, this one is going to cancel with one that's here. And then this one's going to cancel with one that's over 1, 2 up. You see what I mean? And everything else is going to cancel. And you have to be able to examine now, well, what survived? Well, this. 1 will not cancel with anything. 1/2 will not cancel with anything. And then these 2 survived in the nth stage. So this allows you to write that the partial sum, S of n, is equal to everything that survived in blue. So this is 1 plus 1/2 minus 1 over n, lowercase n, 1 over lowercase n, minus 1 over n plus 1. So those are the 4 terms that survive. Everything else in the middle of this telescoping series canceled out. That's why it's called telescoping. And then we know to find the sum of a series, we take the limit as n goes to infinity of the partial sum. So we did the limit as n goes to infinity of 1 plus a half is 3 halves, minus 1 over n minus 1 over n plus 1. So you take the limit of what's left. Each of these, you have a fixed number over infinity for both of them. They both go to 0. So you get that the limit is 3 halves. So 3 halves is the answer to this problem. It converges, and the sum of all of them, if you continue this list forever, would be 1.5. So that's the idea of telescoping. The biggest piece of advice I could give you is to organize your work. And don't be afraid if things don't cancel right away. Just follow this method, and you should be good. All right, well, let's look at this sum now. So this should look fairly familiar to you, at least this first one. So this is equal to the summation, and I'm going to break this up into 2 problems. So you have the first thing here, this 2 over n squared minus 1 plus, and then I'm going to focus on the second one, which is 1 over 4. And I can write it like that instead. I have 1 over 4 to the n is the same thing as this. Now we just solved this problem. This is the one we just did. This right here, that was 3 halves. So we're done with that. What type of series is this? I have some fixed number r raised to a power. This is a geometric series. We just did that recently in one of the previous videos. And the absolute value of r is the absolute value of 1/4, which is less than 1. So we know that we converge. And when you converge, you can use the formula. So just this right here, if you wanted to find the answer to that, I have all this space over here. I don't know why I'm not using it. So let me go over here and use this space. So just this piece, summation n equals 2 to infinity of 1/4 to the n is, the formula is first term over 1 minus r. So first term, if you plug in 2, that's your first term this time. Plug in 2, that's going to be 1 over 16. That's what happens when you plug in 2 for that. And then it's 1 minus, and you plug in 1/4. That's my r value. So we get 1 over 16 over 3/4. This, if we flip that around, that's 1/16 times 4 over 3. And we get a cancellation here of a 1 and a 4. Looks like I get 1/12 just for this part right here. So since it's 1/12, and I know this one here is 3 over 2, the answer is just we add these two together. So this is, so the final answer, so I'll say the final answer is going to be 3 halves plus 1/12. Are we really going to make me do this difficult math? OK. So if you multiply by 6, you get 18 over 12 plus 1 over 12, which is 19 over 12. So the final answer there is 19 over 12. OK, so what I just did here leads itself to some properties that I want to talk about. So this last example illustrates that if you have 2 convergent series, so my 2 convergent series were each of these individually that I split it up into, then the following things are true. And you have c as some constant too, by the way. So you have that the summation of the 2 series is equal to the summation of each series separately. Like I did, you can break it up. Same is true if you are subtracting. So if I have 2 different terms being added together, you can split these up into one series minus the other series. Doing that might help with your calculations. And the last thing I'll say is if you have a constant times some convergent series here, or the terms are c times the series, then this is equal to, you bring the constant out, and then you just evaluate the convergent series. So all those rules are true. All right, now what I'm going to do is I'm going to give you some final examples. So let's look at this first one. So we're going to figure out if the series converges. If it does, we're going to find the sum. Here's my first one. You might want to pause the video as I do these and think about them. So the first question we have to decide is if it converges or diverges. If it diverges, we're done. We don't have to do anything else. So the test that I'm thinking we're going to use for this is I'm going to use the test for divergence from the last video. If I can, this is probably the first test you should always try if you're suspicious. It's the quickest one, and it helps you finish the problem. So I need to take the limit. Here's my a sub n. I need to take the limit as n goes to infinity of the nth root of 2. Now, I know that that's 1. I'm probably going to show you right now. I should be a good teacher, right? I should show you why that's 1. So let me show you why that's true, just in case you forgot that. So let's say f of x is going to be the xth root of 2, which is the same thing as 2 to the 1 over x. OK, so what I want to do is I want to figure out what the limit of that is as x goes to infinity. So let's say y is the limit as x goes to infinity of 2 to the 1 over x. I'm going to take the log of both sides. So we'll have ln of y equals, bring the log in front. Bring the 1 over x in front of the log. You'll get the limit as x goes to infinity. You can take the log of 2, and remember the power goes in front of the log based on log properties. So I get ln of y is, this right here is ln of 2 over x. So ln of 2 is a constant. The bottom goes to infinity. So overall, this limit right here goes to 0. And then if ln of y is 0, take e on both sides. And this means that y equals e to the 0, or 1. So my original limit should have been 1. So this is just kind of like an aside. Anyway, so because the limit of this a sub n is 1, that's not equal to 0. So that means this diverges by test for divergence. Remember, if you do not get 0, you say it diverges. If you get 0, you say, I don't know, and then you try a different test. And we're building up all these other tests that you can try now. New example. How about summation n equals 1 to infinity, 3 to the n plus 2 to the n over 6 to the n. So you could try this if you want. I will go ahead and try it now. You can use this idea that I just talked about above. Let's split it up. So this is the summation of 3 to the n over 6 to the n plus the summation, n equals 1 to infinity, of 2 to the n over 6 to the n. You could do two smaller problems. So instead of having it like this, remember, you can just put 3 to the 6 all raised to the n. And this one right here, if they're both raised to the n, it's 2 over 6 all raised to the n. So I'm just going to write it prettier. 3 over 6 for this first one, that's a half. So this first one's going to be 1/2 to the n plus, and then this one is 2 over 6, so that's 1/3 to the n. And then for each of these smaller ones, I'm going to think about the infinite geometric sum, because both of these are geometric sums. Both of them have r less than 1, absolute value of r less than 1. So what I'm going to write here is just a reminder. It's the first term over 1 minus r. Remember that. That's a flashcard. First term, I plug in 1, and I get a half. And then 1 minus r is a half, plus. First term here, plug in 1, it's a third. 1 minus r is a third. This is a half divided by a half, which is 1. And this is a third divided by 2/3, The 3's cancel and you get a half, so 1 plus a half is 3/2. So not only do we know it converges, we know the exact sum. So this sums up to 3/2. I'm going to fit one more example right here. I'm just going to go down on here and just hope I have room. There's not much for me to say here. So this is the summation of 3 over 5 to the n plus 2 over n. OK, so here you could try to split this up. So what I could do is I could write this as 2n equals 1, n equals 1 to infinity, 3 over 5 to the n, plus n equals 1 to infinity of 2 over n. The problem is you actually can't do that, because while this right here is a geometric series, this is not. So right here, remember that you can bring a constant out front. So this is n equals 1. There's 2 times. So just this series right here is n equals 1 to infinity 1 over n times 2. And do you remember all that work I did to show what happens to this series? This is the harmonic series, right? So this second series diverges. In fact, this goes to infinity. And if I multiply it by 2, this just like very diverges. It's even larger. So out of these two terms from the beginning, this diverges. It doesn't matter that the first one converges. They both need to converge to be able to add these together. So because the second one is divergent, it's harmonic, the whole thing diverges. And that's it. OK, we are building up our list of examples here. In the next video, we're going to start a lot of different tests for showing whether series converge and diverge. So I will see you in lecture 19 when we talk about the integral test. Have a nice day.